Hello everyone, my name is Tashwanti. I am a graduate student from the Department of Electrical Engineering, IIT Madras. Today I would like to present upon the capacity of photonic erasure channels with detector dead times. This work is jointly done with Professor Krishna from IIT Madras. I would like to start with what a photonic channel means. A photonic channel is the one in which the information is encoded with photons and transmitted. At receiver, a single photon detector, referred to as SPD, which is an extremely sensitive device, is used to detect these photons. An ideal detector is the one that detects all the photons without any errors. Errors, I mean, it should not miss any detections, it should not have any false detections, and all the information should be decoded correctly. Often, no detector is ideal, and it is known that the detectors are characterized by a non-zero dead time. Dead time, I mean an insensitivity period during which the arriving photons cannot be detected. In this talk, we consider a setting where classical information is encoded with photons and transmitted over a photonic communication channel. We say that the detector has a non-zero dead time and assume that the information carried by the lost photons is erased. If multiple photon arrivals happen during the dead time, the detector often tends to produce bursts of erasures in the detected sequence. We see that there are two classes of detectors, namely NP-type and P-type, and define a class of photonic erasure channels where we specifically consider the arrival process to be a Poisson process. Next, for any of the types of detectors and any general distribution of dead times in the system, we derive the fundamental limits on the rate at which classical information can be transmitted over a photonic erasure channel. To motivate the problem further and to understand the notion of dead times clearly, let us look into the physics of the detector. Here is one frequently used detector referred to as silicon photon avalanche diode, also known as SPAD. An SPAD is just a PN junction diode operated at voltage greater than the breakdown voltage of the diode. At this voltage, the electric field inside the diode is so high that even a single photon particle that hits the diode causes an avalanche of current to flow in the circuit. This spike in current is used to record a detection in the system. In order to detect another photon, the operating voltage should be quenched. Quench, I mean reduce the voltage in order to reduce the avalanche current, and the voltage should be raised back above the breakdown voltage of the diode. This time that the diode takes to quench the voltage and raise back is called the dead time of the detector, during which an arriving photon cannot be registered. Hence, the detector tends to cause multiple erasures in the detected sequence, and we call such a channel as the photonic erasure channel. A table of typical dead times in various photon detectors has been displayed below. In general, any detector typically exhibits a dead time of 20 nanoseconds to 100 nanoseconds after each photon detection. Further, based on the physical realization of the detector, the detectors are classified into two types. One, non-parallelizable, referred to as NP-type detector, where any arriving photons during the dead time of the detector has no effect on the dead time. That is, as an example, consider the following setting where the detector goes dead for a period d1 after first photon absorption. In an NP-type detector, any arrivals during the dead time d1 are not registered and the information carried by those arrivals is assumed to be erased. Similarly for the next. The arriving photons have no effect on the dead time and information carried by that photon is assumed to be erased in an NP-type detector. On the other hand, we have a parallelizable or P-type detector where an arriving photon during the dead time restarts and extends dead time by a new independent realization. Example, in the same setting as before, where the detector goes dead for a period of t1 after first photon absorption, in a P-type detector, any arrivals during the period t1 restarts and extends the current dead time by a new independent realization. Similarly for the next detections. In our work, for both these types of detectors, we try to address the question what is the maximum rate at which information can be transmitted in such photonic systems where erasures happen due to the dead times of the detectors. The problem of dead times in photon counting systems has been dated back to the 1970s, where Mueller introduced the notion of dead time and summarized the statistical results the systems with various arrival distributions of photons in 1981. Further to this, a lot of research has happened in statistical analysis of photon counting systems for different applications such as LiDAR, imaging, and others. Later in 2009, with the advent of more sophisticated photonic detectors, the effects of dead times in the system became more prominent, where researchers started to analyze the system and come up with efficient transmission strategies to mitigate the loss incurred due to the dead times in the systems. One such successful attempt was done by RAP in 2019 to reduce the losses due to dead time effects in high flux imaging. There have also been similar attempts for the same in other applications. In our work, we try to build upon the previous statistical analysis and intersect it with information theory and derive the fundamental limits on rate at which information can be transmitted in photonic communication systems. To the best of our knowledge, this is the first recent work to consider the effect of dead times in modern timing photonic devices and characterize the rate at which information can be transmitted. Going to the system model, we consider a binary input code word where information is encoded with photon polarization states and transmitted according to a Poisson process of rate lambda. At the receiver, if the detector is on, it decodes the information correctly, or otherwise, if the detector is dead due to previous photon absorption, it produces erasures in the detected sequence. An animation for the same is shown here. Other notations, we use the sequence AI to denote the inter-arrival times of the photons, and the notation DI is used to represent the dead time of the detector caused due to ith photon absorption in the system. For the above system model, we first consider a simpler setting where dead times are IID exponential random variables with rate mu. In such a setting, irrespective of the detector type, the capacity is shown to be lambda times mu over mu plus lambda in bits per second. The proof follows by first showing that the channel reduces to the binary erasure channel with erasure probability lambda by lambda plus mu irrespective of the type of detector in the system. We then use the classical capacity result of binary erasure channel, which is 1 minus epsilon, where epsilon denotes the probability of erasure to obtain the capacity. Further, it is known that uniform IID input distribution achieves the capacity of a binary erasure channel. We next consider a setting where dead times are deterministic for a fixed time period Td. In case of an NP-type detector, as the photon arrival process is Poisson process, it can be seen that each detection is followed by an erasure burst whose burst length is Poisson distributed with rate lambda Td. We show that the erasures in this setting are not memoryless, and the induced erasure channel is defined by the sequence of conditional probabilities, probability of yn given xn. It is really challenging to solve this problem because the erasures are correlated. However, we see that the channel is stationary and information stable. That is, any input in the system produces an output with stationary distribution. Hence, the mutual information is sufficient to calculate the capacity, and the general capacity expression given by Verduhan is applicable here, which is as n goes to infinity, 1 over n maximum over all the input distributions I of x and yn, where I of x and yn is the mutual information between input and the output sequences. As we make lambda channel uses per second, the factor lambda is multiplied to get the capacity in bits per second. Using this result, we have the capacity as lambda times 1 over 1 plus lambda Td in bits per second, which essentially says that we are transmitting one correct information bit among 1 plus lambda Td information bits, ignoring the lambda factor. The proof of this theorem follows by showing that the n-fold channel is quasi-symmetric which tells us that the capacity is the expected number of unerased bits in the sequence. We then apply elementary renewal theorem to obtain the closed form expression. Furthermore, it is known that uniform IID input distribution achieves the capacity for quasi-symmetric channels. This result of the deterministic case and NP-type detector can be generalized to a setting with NP-type detector and any general distribution of dead times where the capacity is shown to be lambda over 1 plus lambda times expected dead time duration in bits per second. The plot on the right side depicts that in a system with NP-type detector, fixed photon arrival rate decreases the capacity with increase in expected dead time duration, and fixed expected dead time duration increases the capacity monotonically with arrival rate and saturates at 1 over expected dead time duration. Finally, for a setting with p-type detector and any general distribution of dead times, the capacity is shown to be lambda times the Laplace transform of dead time distribution evaluated at point lambda. The proof of this goes by reducing the channel to binary erasure channel with erasure probability 1 minus Laplace transform of dead time distribution at lambda. Unlike NP-type detectors, in p-type detectors, the capacity depends on the entire dead time duration through its Laplace transform. And we show that using Jensen's inequality, that the deterministic dead times have the least capacity. To summarize, we have introduced a photonic channel where classical information bits are encoded with photon polarization states. We have briefly seen the notion of dead times of single photon detectors and different types of detectors. We have also defined a photonic erasure channel with dead time induced burst erasures, and finally derived the single letter capacities for different settings considered. We finally inferred the following results: that for an NP-type detector in the system, for fixed photon arrival rate, the capacity decreases with increase in the expected dead time duration, and for fixed expected dead time duration, the capacity increases monotonically with arrival rate and saturates at 1 over expected dead time duration. In contrast, for a p-type detector in the system, the capacity depends on the entire dead time duration through its Laplace transform. Future work. Our future goals are very clear. So throughout this paper, we consider the dead time process to be Poisson and assume that we have no control over it. One direction is that we can look into different traffic shaping strategies to improve the capacity by mitigating the losses. Also, in this work as an initial setting, we consider the channel to be ideal where there is no noise. Another direction to our work is to look into more realistic channels like noisy channels. Though it is hard to consider, it would also be a challenging problem to consider more realistic deletion channels instead of erasures where we do not have the information about lost photons. Lastly, I would like to emphasize that the transmission of information over photons is inherently a quantum phenomenon, and for simplicity in our study, we considered an easier setting of transmitting classical information. One can think of a more challenging problem where we try to find the fundamental limits on quantum correlated erasure channels. I would like to conclude this talk by saying that the dead times of the detector may not be avoided, but a better control over photons and optimal coding strategies can always be implemented to mitigate the loss and improve the capacity of photonic systems. Thank you.